So in this talk, I'm going to talk about the time-space trade-offs for finding a long common substring. So the work was done with Shai Golan, Thomas Kochumaka, and Matan Kraus. Okay, so this is a very common problem. So the idea is to, given us two strings S1 and S2 of total length n, we would like to find the longest common substring of both S1 and S2. So in this example, you can see that BABC is the longest common substring. So a classic solution to this problem was introduced with the discovery of suffix trees back in 1973. And the idea is to create the joint suffix tree of the string S1 and S2. And then by some traversal over the tree, bottom up, we can identify all the common substring, and of course, we can return the largest. And it costs order of n time and order of n space. So why do we care about this old problem? So the idea is that order of n space might be too large, and we would like to restrict it. So looking at some previous works, in addition to the strings, we also get a parameter s, which restricts the space usage. So some of the previous work by Staryovkovskaya and Vilhoy given this result for the parameter s in between n and 2/3 and almost n to the 1. And the space is order of s, and the time is order of n squared over s plus s times log n. And it was later improved by Kochumaka, Staryovskaya, and Vilhoy to such that the time will be order of n squared over s, n squared over s. And in our solution, we stick to the same space, of course, and we improve that the time will also be divided by the real length, by the actual length of the longest common substring. So if the longest common substring is quite long, then it's a big improvement. So in this talk, I'm gonna give a layout of the solution in high level, and we start by solving some problems first. So we start by looking at the LCAS problem, which is the longest common uncoded substring problem. So the idea is that in addition to the string S1 and S2, we are also given some the sets A1 and A2, which are encores, or essentially they are positions in S1 and S2. And we say that some common encode substring is taking an anchor from S1 and taking an anchor from S2, and we extend it as most as we can to the right and to the left. And we are wish to find the longest common encode substring. So in this example, you can see that there are several common encode substring, but the longest is the red and purple one. So the problem here is that even if you can take a pair of positions and return in constant time what the maximal extension to the right and to the left, we still need to go over all the pairs of encores, which is can be n to the square, and it's quite a long time. So we would like to have an efficient solution to it. So for that, we are gonna take the sets A1 and A2, and we are gonna create some other sets, P and Q, from them. So for every index, for example, in A1, we would like to add a pair to P, a pair of strings, which is the prefix of S1 that ends in I, reversed, and the suffix that starts from S1 at I to the end. And we do the same for Q for S2. And now the idea is that given that we have these new sets, we would like to find a pair from P and a pair from Q that give us the maximal LCP, which is the longest common prefix for the first string and the second string. So you can see here in this example that the second pair from P and the second pair from Q give us LCP of 1 for the first string and LCP of 2 for the second string. And this is the longest, which comes up to combined LCP of 3. So here, the thing is that solving this problem is essentially, again, going over all the pairs. But apparently, Charles and Popoulos et al. Has introduced, has formalized some technique by Kroshmore et al. And Fleury et al., which is also used for similar LCS problems. And basically, it's exactly what we need. The input to the problem is P and Q, and the output is exactly what we need. But the problem is that also the input here requires some compact trie of the family strings, of a string family F, which is basically a trie of all the strings in P and Q combined. So how can we create this trie? So just a quick recap about sparse suffix tree. So in a regular suffix tree, for example, for this string, we are creating the tree for all the suffixes. So you can see that we have all the nodes that represent all the suffixes. But in a sparse suffix tree, we would like to select only some of the suffixes. For example, these 3 suffixes, which means that only these 3 nodes will remain. So for example, for this illustration, we delete this tree and we remain with this compact trie. And of course, it's compact because on the edge, you can see that we have a full string and not only a single character. And Birenzweig et al. Showed that this such sparse suffix tree, given a single string S and a set of positions B, can be constructed in order of n log n time and order of B plus log n space. So this is exactly what we need for solving the LCAS problem. So to summarize it, we create P, Q, and F, which is the sparse suffix tree for the combined all of the strings. And we have a reduction to the 2 strings family LCP problem. So it ends up that we can solve the LCAS problem with a complexity of n log n time and almost linear space. So now we are getting to an additional problem, which is called the LCS-L problem. And before we're going to solve it, we're going to look at some definitions, which are runs and Linden roots. So a run in a string is a substring x, and it's called a DP run if the length of x is at least d, and the periodicity of x is at most p. And of course, inside S, the substring x cannot be extended more to the left or to right without breaking this period. Just as an example, there is the string S, and there is, for example, the 10-5 run x, which is from the index 3 to 13. And we define the Linden root of such a run x to be the lexicographically smallest rotation of a period of x. So for example, here you can see that the period is ACAB, and if you look at all of the rotations, which are those, the minimal rotation will be AB and C. And it will be used later to create some synchronization. And we note that as long as D is at least 3 times P, then of course, the number of DP runs is at most N over D, because length of each run is at least D. And those runs, along with the period lengths and Linden roots, can be enumerated in linear time and constant space. So now back to the LCS-L problem. In addition to the string S1 and S2, we are also given an integer threshold L. And the idea is that we would like to find a common substring G, which has the length of at least L. So we would like for LCS-L to return to us is that if the true LCS is between L and 2L, then we would require it to return a common substring G that has the length of at least LCS, because of course there can be several common substring which has the length of LCS, the maximum length. And if LCS is bigger than 2L, then we don't really care as long as it returns some common substring G that has at least the length 2L. And we solve this problem with a reduction to the LCAS problem. So the idea is that if we have two strings S1 and S2, and we have some common string inside it, we would like to choose some anchor into A1 and a synchronized anchor for the first anchor into A2. So for such that then the LCS problem will find this as an anchored common substring. So the idea is that if the common substring start at position I in S1 and position J in S2, then we need some offset K such that I plus K will be in A1 and J plus K will be in A2. So how can we how can we do it for all the substring that interests us? So what we need is a set of, so let's start with a single string. So for a single string, we need some set of positions P, which is not so large because we have we're gonna have a space rejection soon. And we want it to have the following properties. So for every string T of length L or above, we want to choose at least one position into P. And if this occurrence of T resides once again inside S, then we would like to add a relative position to the first position we have added into P. And for that, we have the nice partitioning set by Birnzweig et al., which gives us exactly what we need. So a tau partitioning set for a single string S has the properties that it's quite compact, meaning that it will choose an index not so far between each other, at most tau, unless, because of some issues, unless the string at this block is quite periodic. And the second property is the local consistency, which means that I is inside P is depend only on the block, only on the area that's around I. So for example, if I here is taken into P, and J here has the same area around it, exactly the same, then if I is inside P, then J has to be inside P. Okay, so what we do is we create some partitioning set, some fifth L partitioning set P of the string S1 concatenated with S2. And we just create the sets A1 and A2 from P. So the idea is if P is less or equal to the size of, to the length of S1, then take it to A1, and otherwise take P minus the size of the length of S1 into A2. And the intuition behind it is that if we have T, which is a common substring in S1 and S2, then because it's a fifth L, then for sure in the middle part of T, because of the compactness property, then some position will be taken from the middle part. And because it's exactly the same string in S2, then we will also take this relative point into A2. And this was the non-periodic case because, as we said, the partitioning set doesn't provide us with positions in periodic strings. So without going much into that, the idea is that we also would like to go over all the runs. As we said, we can do it in linear time and constant space. And we would like to have to add these 4 points. So we add the first and second position of the linear root, and we would like to add the boundaries, which is the start position and the end position of this run. And the idea is that if T intersects with this run, then taking the end position, both in, of course, in S1 and S2, if we take the end position of the run, then it will be an synchronized position. And if t is entirely resides within the run, then we can look at the leftmost position of t inside the run. And we can see that taking the Linden route, here it's the first and here it's the second, we can see that it creates a synchronized position. Okay, so to summarize the LCSL problem, we're just combining all the encores from the partitioning set and from the periodic case. And Birenzweig et al. Also show us a deterministic algorithm that constructs a d log star n partitioning set in order of n log d time and order of n over d plus log d space. So by choosing d to be some theta of L over log star n, we can create the fifth L partitioning set, and we get a solution in order of n log n time and O tilde of n over L space. So it's very nice. But the thing is, we would like to restrict the space taken by the LCS problem. So we introduced another parameter. We introduced the space times trade-off for it, and we are taking another parameter S. And the naive idea is to split S1 and S2 into overlapping substring, just naively, and in the size of M, where we take M to be N, the minimum between N or LS over log star N. And this basically means that now we have many instances of S1 and S2, and we just go over all the pairs. So now we have N over M to the square pairs, and each pair is calculated over a string of length order of M. Therefore, the space complexity is, if we are looking at the previous LCS L solution, it's order of M log star N over L, which is basically order of S, and the running time is, because we are going over all the pairs, and for each pair it's M log M, and we end up with O tilde of N squared over LS, plus N, of course, because of the minimum. And this ends up to be the main result. For the main result, what we want to do is, we don't actually know the length of LCS, so we would like to take some guesses. And we would like to run the LCS-L algorithm with exponentially decreasing guesses of L. So we start by going L is equal to N, and then N half and N fourth, and etc. And the idea is that we stop when LCS-L returns a common substring of length at least L. So why does this work? The idea is that when we stop, then LCS, the real LCS, will be between L and 2L. And then LCS must return a longest common substring, some substring that has the length of the real LCS. And of course, as long as we don't get to the last iteration, then our guess is larger than LCS, and of course, LCS-L can't return a common substring that is larger than this guess L, or equal. And overall, the complexity of it is O tilde of the space, of course, is order of S, and for the time we're getting a regression and because if we're iterating, then we get that the time is dominated by the last iteration, which ends up to be O tilde of order of N over the size of LCS times S plus N time. And that's it. And thank you, everyone. Thank you for watching.